Hi, it's Mr. Baker with another physics video. Today we're going to be looking at seismic waves. Okay, so today we're going to be looking at seismic waves and we're going to be answering this question. What evidence is there for the shape of the Earth? So where do earthquakes come from then? So seismic waves come from earthquakes. The black dots on this map of the world depict where earthquake activity is occurring. You can see that, as with volcanoes, the earthquakes are not randomly distributed around the globe. Instead, they occur in linear patterns associated with plate boundaries. At the boundaries between plates, friction causes them to stick together. When built-up energy causes them to break, earthquakes occur. Movement and slipping along these types of boundaries can form an earthquake. Earthquakes may also occur in volcanic regions and are caused there by both tectonic faults and by the movement of magma, hot molten rock, within the volcano. Such earthquakes can be an early warning of volcanic eruptions. So there are three different types of seismic wave. The first seismic wave are the P waves. So these P waves are longitudinal waves. You can see that the particles are moving in the direction of the propagation of the wave. So this is what a longitudinal wave does. These are the first types of wave that would reach us in an earthquake. They're sometimes called pressure waves. The second type of seismic wave is the S wave, and these are called the secondary waves. They arrive second from the epicenter of the earthquake. They're slower waves and they're transverse waves. And these waves do more damage. You can see them shaking the earth around them as the particles move at right angles to the direction of the wave. When these waves both hit the surface of the earth, then we get love waves travelling along the surface. These are the most damaging of the seismic waves. And you can see that they shake left and right and up and down. They're the third type of wave that arrive after an earthquake. So how do we know what the Earth is made of? So if we can't go to the centre of the Earth, except in science fiction movies, how do we know what the internal structure of the Earth is like? We need to use geophysical imaging techniques to model what's going on below our feet. Seismometers are used to measure the vibrations that can be detected from earthquakes around the world. So this image is of a seismometer, and you can see how it might work. We have a heavy mass suspended from a spring, which stays relatively still. Then we have the seismograph paper, and this is called a seismogram. And when there are vibrations, this moves up and down, and the pen stays where it is, recording those different vibrations. So we can see the size of those vibrations by how far up and down those pen marks are, and we can see how quickly those waves are moving because it's recording time as it goes round. So this is an image of a seismogram. You can see the y-axis shows the amount of ground movement, and the x-axis shows the time. So the seismograph paper moves towards the left in this diagram. So you can see where the P wave arrives first, and you can start seeing the shaking of the up and down. And then you can see the SP time interval. So this is the time between the P wave and the S wave, where the secondary wave arrives second after the primary wave. And you can see the time between that, and that would be the SP time interval. And then the third wave to arrive would be the surface wave, these love waves, and they cause the most vibration. So from a seismogram then, we can tell quite a lot. We can tell the size of the earthquake, and we can tell the time it's taken to arrive at different places around the Earth. And it's this information that we use to find out what the structure of the Earth looks like. So here we've got two diagrams. Both diagrams show the structure of the Earth. The diagram on the left shows where S waves have been picked up around the Earth, and the diagram on the right shows where the P waves have been picked up around the Earth. Now when there is an earthquake, seismometers around the world detect the vibrations. But what they detect is that there are certain places that waves of certain types fall. But what they detect is that there are certain places that waves of certain types don't fall. These are called shadow regions. Both sets of waves seem to curve towards the surface. This is because their speed changes with depth. You can see from the diagram on the left that the S waves aren't detected the other side of the Earth. They don't reach the opposite side of the Earth, and there is quite a big region either side of this that they don't fall to. This is because S waves are transverse. They can't travel through liquids. From the evidence that S waves don't travel to nearly half of the Earth, we know that there must be a large liquid section in the Earth. The outer core is molten iron, liquid. You will also see that from the P wave patterns, they all travel all around the Earth, but not in straight lines. This is because P waves are longitudinal. They can travel through liquids, and they can travel through solids, but they'll travel different speeds through different densities of materials and even refract. Geologists know the speed that these waves will travel through different objects. The Earth is made up of three main layers: the core, the mantle, and the crust. The interior of the Earth is divided into layers based on chemical and physical properties. The Earth has an outer, silica-rich solid crust, a highly viscous mantle, and a core comprising of a liquid outer core that is much less viscous than the mantle, and a solid inner core. Working from the centre of the Earth out, we have the inner core. This is primarily solid and about 1,220 kilometres in radius, situated at the Earth's centre. The inner core is believed to be composed primarily of a nickel-iron alloy. The liquid outer core is 2,300 kilometres thick, and like the inner core, is composed of a nickel-iron alloy, but with less iron than the solid inner core. Evidence indicates that the outer core is so hot that the metals are in a liquid state. The mantle is approximately 2,900 kilometres thick and comprises of 70% of the Earth's volume. The core makes up about 30% of the Earth's volume, with the outer crust, where we live, less than 1%. Due to the temperature difference between the Earth's surface and outer core, convection currents are set up in the mantle. Hot material rises up as the mantle plumes like a lava lamp, while the cooler and heavier material sinks downward to be reheated and rise up again. The outermost layer is the crust. This is the most familiar to us as it's where we live. The distinction between the crust and the mantle is based on the chemistry, rock types and seismic characteristics. So this is what we've done in this lesson. These are the things you should be able to do. You should be able to describe what seismic waves are and how they're caused. You should be able to describe the internal structure of the Earth and compare the three types of seismic waves in terms of speed they travel and whether they are transverse or longitudinal. You should be able to explain in detail how the internal structure of the Earth can be determined by the waves passing through it, and you should be able to interpret seismograms. So that's the end of today, and we asked this question: what evidence is there for the shape of the Earth? So from the evidence that seismometers pick up around the Earth, we know that there are some regions that S waves won't reach, and that's because they won't go through liquids. So we can conclude that there is a liquid section to the Earth. We can also see that P waves don't reach some places, the P wave shadow regions. They will refract through the Earth's centre as well. And this is because the Earth is made of different density materials, and so the waves are travelling at different speeds. So geologists have got a pretty good idea of what the Earth's made of because of these seismometer readings that they've picked up from around the world. But until Elon Musk decides he wants to go to the centre of the Earth, we'll have to make do with these conclusions. Okay, so that's been another physics video all about seismic waves. I've been Mr. Baker, and I'll see you next time. Thanks very much.